Good evening, everyone. You're welcome to CHM204 class for tonight. My name still remains the same, Professor Olayinka Ajani. I am your facilitator for this course. Last week, we talked about the topic 1 for the week 1 of the facilitation. 1 week is gone. Today is another edition of the live class for CHM204. You have to watch the video sent to you previously before every live class, so that we can have the opportunity to tackle these challenges and the problem you may have in that video. Because the video that was sent to you before the live class is exactly what you have to learn and what we have to know for that live class. So when I send it to you, please, due diligence is required of you to watch this video and the instructional material so that is loaded. This video put forth to you on the virtual learning environment, which is a course page, in form of a link. When you click the link, it will take you to where to watch that video. So waited a little for some people to join us. But for now, we have to start the class anyhow. I believe they will be joining us and other people that have not yet come on board. It is important for us to tell them from time to time that the live facilitation has started for this session and that we all need to take a very good advantage of it to facilitate our learning and give us a better comprehension, which in turn will lead to outstanding performance for this course. Thank you very much once again, and you are welcome on board for today's live class. Today, in our CHM204 titled The Structure and Bonding, a 2-unit course, we are going to the topic 2, which is for the week 2 of the live class. At the end of this unit 2, learners should be able to, 1, understand the valence bond theory of bonding in molecule. 2, you should be able to know how orbitals are mixed through hybridization in order to form bond. They should know the different type of hybridization and provide example for each. They should understand the molecular orbital theory and the application in explaining bonding. They should be able to differentiate between bonding molecular orbital and anti-bonding molecular orbital. They should understand how pi and sigma bonds are formed. They should know molecular orbital theory and know how to use it to calculate the bond order and interpret the properties. They should be able to solve mathematical problems that are associated with the theories of bonding. So today's in topic 2, looking at the theory of bonding. In topic 1, we've looked at the chemical bonding. As an example, we looked at the ionic, or otherwise known as electrovalent bonding, and we looked at the covalent, otherwise known as the bonding that exists in organic molecule as a result of sharing of electrons. Today, we are going to be looking at some of the theory of this chemical bonding. There are 2 methods used actually for the calculations of molecular structures. The first one is valence bond theory, VBT, and the second one is molecular orbital theory, which I have put as the acronym MOT. Yes, briefly, what is VBT? Valence bond theory is actually based on the Lewis concept of electron pair bonds. However, the molecular orbital theory relies solely on the combination of atomic orbitals to form the bonding and anti-bonding molecular orbitals. So former stabilizes the molecule, while the later ones actually destabilizes the molecule. Valence bond theory. Valence bond theory considers that a bond is actually formed when an electron in an atom, atomic orbital of one atom, pairs its spin with that of an electron in atomic orbital of the another atom. For example, in molecular hydrogen, there are 2 atoms of hydrogen that are involved. When you are talking about molecular hydrogen, you know that there are two hydrogen atoms that are involved. What I mean by that is that an hydrogen molecule is formed from the overlap of two different hydrogen atoms. You know, each hydrogen atom have one s1 electron, which means there's only one electron in the valence shell of the hydrogen, but hydrogen needs two electrons there to form a duplex rule. So when that happens, the first hydrogen, you will use one electron, maybe to spin up. Is looking for one more in order to complete a pair. So the second one can share with him covalently by pairing his own electron down close to him. So in that case, the first hydrogen is enjoining duplex rule by the two. This is an equivalent example of sharing. And the second hydrogen is also experiencing the enjoyment of stability by the two electrons, which is a pair. So what we are saying is that a pair of electrons is made up of two electrons, one donated by each atom, and it now forms a ray bond. If hydrogen number one has donated one electron, and hydrogen number two is donating one electron, by the time they share it together, we form a single line bond between them. And that's what causes the formation of hydrogen molecule. So we are looking at, for example, the molecular hydrogen, which has one electron in the first hydrogen atom and one electron in the second hydrogen atom. The spatial wave function for the electron in each of atom can be written carefully. This is the wave function. There are two of them. The wave function for the first hydrogen, the wave function for the second hydrogen. Because there are two different hydrogens, they have their orbits separated. And the distance between the center of their nucleus to the circumference of their orbit is their radius. So for the first hydrogen, which is H1, the radius will be R1. And for the hydrogen, which is H2, which is the second H, the radius will be R2. Now, when we are dealing with this, because the two of them are relating together, the two atomic orbitals comes together to form the molecular hydrogen. So it means that there will be relationship between the wave function of the first as having the first density of electron relating with the wave function of the second, which is the B atom, having relationship with that. So in that note, valence bond wave function of molecular hydrogen can be easily written as interaction between the first to the second and interaction between the second to the first, because the first one is donating its own electron for the second to form a pair of electron around themselves, obeying duplex rule for a better stability, while the second one is also lending its own electron to be shared by the first hydrogen in order for the first hydrogen to also obey the duplex rule. And that's the reason why we are saying the total number of atomic orbitals that is combined will be total number of the molecular orbital that we will get. The first hydrogen atom combined with second hydrogen atom, so you are expected to have two molecular wave combinations. You can see the wave combination with the reference to the hydrogen of the A atom sharing from the B atom to form its duplex, then the hydrogen from the B atom sharing from the A atom to form its duplex. So you can see that if this is the first hydrogen A, this is the second hydrogen B, hydrogen B obey the duplex because A has given him an electron. Hydrogen A has obeyed the duplex of stability because B has given him his electron. So if two atoms are combined, HA and the HB, then you're expected to have two molecular combination of the wave. The A with respect to B and B with respect to A. So in this perspective, as we have seen, we can carefully see something unique about the orbital combination. And that's what leads us to the nature of orbital combination in valence bond theory. The valence bond theory relies solely on the overlap of the orbitals of the combining atom, just like the orbital of the first hydrogen, HA, combining with the orbital of the second hydrogen, HB, in order to form H2 gas. Therefore, conditions to follow for orbital overlap to occur are, number one, a completely filled orbital cannot overlap. When an orbital is completely filled, let's say, for example, an s orbital, it has maximum of 2 electrons. If it has already have that 2 electrons, it has no space to accommodate anything from outside. And before overlap can occur, somebody has a space to accommodate something from another. Just like the first hydrogen, HA, has only one electron and has a space for one more electron to come in. That's why the hydrogen, HB, can donate to him by that overlap, and vice versa. But when you have a complete pair of electrons required and it's already filled up, there can never be overlap. So a fully filled orbital is stable and therefore cannot involve itself with bonding because it has no space to receive electron from outside. Therefore, it cannot enjoy overlap with any other group. So the two half-filled orbital can overlap to form a new bond. But if it's fully filled, it cannot overlap. Then the second condition is that the atoms with bonding orbitals should be closely and properly aligned with the axis of their orbital. The axis of their orbital is a place where the strength of their electrons are residing. If they are using those places to come close to others, then there will be a strong synergy in the attraction between the two of them to form a real-time strong overlap, which results in a bond formation. But if it's not localized on the axis where there's concentration of the power of that electron, then there will not be strong synergy for them to overlap and attract in order to form bonds. So these two are very, very important. Type of interaction through proximity. We are saying that the closeness is very important and the electron should be on the axis where they are having strong effects, also very important. Now, there are three major types of interaction that can be encountered when atoms come close to each other. The first one is that if they are too close to each other, there will be repulsion between the nuclei. What do I mean by this? You know that inside the nucleus of an atom resides a proton, which is positively charged. So if an atom A has a nucleus that's positively charged, an atom B has a nucleus that is positively charged, when they come so close together, the positive and positive will be so close, and you know there will be repulsion when the two charges are the same. The second thing is that when they are coming too close, the valence shell carries electron. The electron of the atoms of the shell A coming so close to the atom of shell B, both of them are having the electron, and electrons is negatively charged. Both two negative charge will repel. That's another condition. But the third condition is the one that leads to an attraction, which means if the proximity is so positioned in such a way that the interaction that was felt, it was between the electron of the first and the nucleus of the second. Of course, you know in the electron of the first, which reside at the shell of that first, is negatively charged. And the nucleus of the other, which have in itself proton, is positively charged. So the proton and the electron interacting with each other is like a positive charge interacting with negative charge. There will be an attraction. And therefore, in such place, you are able to form bond. Example is that of hydrogen atom that we have looked at before. When you look at the hydrogen atom, the first hydrogen atom is one s orbital. It has only one electron. The hydrogen of the second one is one s orbital. It only have one. When they are brought so close to each other, and they begin to enjoy proximity between each other, there will come a time that the spherical or the shell, the valence shell of this one, which is having the electron, begin to interact with the positive center of the other one. without the positive getting close to the positive. Now, the positive here is getting close to the negative of the shell. What will happen is that there's going to be an attraction. And at that time, there is a molecular hydrogen formed. Because between that two places, where there is overlap between them, is a place of bond formation. And that's why that bond formation is a cloud of electron between them. If this is the hydrogen, and this is the hydrogen, because there is a proximity here that shows the attraction between the electron and the proton, then there is a real-time bond of electron here, forming overlapping on electron here to form hydrogen molecule. Energy diagram for hydrogen molecule formation. If we look at this energy diagram carefully, if you look at this hydrogen as a molecule, you discover that when the hydrogen atom sphere of the first one, of the first hydrogen, is a bit far away of that of the second hydrogen, you discover that, oh, there's no interaction between them. So you can see at A is almost at zero energy if you trace it down. And you know, the lower the energy value, the better the stability, and the better the chances that a real-time bond is formed. Now, when we begin to move the sphere together to close up the gap between them, you discover that as we are moving it so close, the energy is coming down. It's coming down until when they are almost touching each other's side, then the energy has come to negative X. However, there would need for them to touch each other. When they touch, as they are coming so close to each other to touch each other, the energy is getting so low. And you know, the lower the energy, the better the stability, and the more the probability that the bond is formed. It comes to a time perfectly touching each other in such a way that it will not cause any repulsion. Perfectly touching each other means that the shell of this one is feeling the positive charge of the other, and the shell of the other is feeling the opposite positive charge of the first one, which is like neutron, electron and proton interaction. When it comes to that time, you must not allow it to still get too close, because if it gets too close more than that, then the energy level begins to become unstable. So the minimum level at B is the best proximity that can cause a great overlap between the two spheres to form a real bond. Immediately you bring them too much close to each other than that, you begin to see that the proton, which is the nucleus of the first, will begin to come close to the nucleus of the second. And therefore, the proton-proton repulsion will begin to happen. And when that is happening, the energy stability is reducing. Therefore, the energy is coming up to positive. It's coming up to positive. So the best energy state where this thing can be, for that two sphere to come to form a bond, it should be at minimum point of B. And that's the best place. So we are saying that when you are bringing the two nucleus or two shell close to each other, if they are far apart, there cannot be interaction. But as they are getting close, the energy level is reducing and they are getting more strong interaction to form a real bond between them. Until when it comes to a place where B is the best stable form, you stop there. But if you still try to push them inside each other after that B, repulsion begins to happen, which is the first condition, repulsion between the nucleus, because there are protons positively charged there, or repulsion between the electron and electron, because the two shall carry the electron. That will not be a good time for interaction. So the best time for interaction here is at point B, and that there's a real bond formed between the two, and there's a real overlap between them. So overlap. Anytime there's overlapping of two things or two orbitals, I've told you, a bond is formed. But the bond that is formed will be dependent on the nature of the overlap. So based on that, there are two different kinds of overlap that will result in only two different kinds of bond formation. Overlap will result in sigma bond formation, or it could result in the pi bond formation. An atomic overlap that results in a sigma bond are many. When s orbital is overlapping on s orbital, when s orbital is overlapping on p orbital, when p orbital is overlapping on p orbital, all those ones are going to result into a sigma bond. And sigma bond, of course, is strong. But the only unique set of overlap that will result in pi bond is the overlap between two unhybridized p orbital. Let's say there's an hybridized p orbital here there's an unhybridized p orbital here, which means it's not part of the first hybridization. It will be unhybridized, which is 1 electron. If the second carbon atom also have an unhybridized orbital that have its electron, then a secondary overlap can result between the unhybridized px of the first with the unhybridized px of the second. Anytime this happens, it's called pi bond formation. So sigma bond simply, therefore, result from an axial overlap, because the axial or the axis of the electron is where their strength are concentrated. Is where their strength are concentrated. If you can look like this is the axis of this p orbital is along this, axis of this p orbital is along this. So if there is an overlap between this place, then that's where their axes are concentrated. So what you form there is a strong bond and it's a sigma bond. However, if it is a orbit unhybridized p along its lateral nature, you see, it's not at the axis, it's at the side by side, just like two people are gummed together head to head and leg to head. They will not be as stable as when they have their strength concentrated. So when you have this kind of people, when you push them, they will fall. So this is formation of a pi bond. So in that case, the formation of sigma bond type makes it to be very strong because it's as a result of axial overlap, and the formation of the pi bond make them not to be as strong as sigma because it's a lateral overlap. So when you have a bond, so for example, if you have a carbon single bond, as you have in alkane, this single bond is a sigma bond. That's why alkane is strong and cannot undergo a lot of additional reaction. But if you have carbon double bond, as we find it in alkane, every time you see double bond, it means the first bond that was formed is a sigma bond. Then the lateral overlap will occur between the secondary orbital, and that will be pi bond. So a double bond carbon-carbon is made up of, therefore, 1 sigma bond plus 1 pi bond. However, if it is a triple bond, whether carbon-carbon or carbon-nitrogen or nitrogen-nitrogen, anytime you have triple bond, it's also overlap as occurred there. But that overlap means the first thing here is a sigma bond. Then the second one is a pi bond. And the third one is a pi bond. So anytime you have triple bond is made up of 1 sigma bond and 2 pi bond. So let's note all this one, either carbon-carbon, either carbon-nitrogen, either carbon-oxygen. So but I've used carbon-carbon here so that you can see the difference between 3 different of hydrocarbon. The one that have single bond is ending with a suffix called -ane. So they are alkane if it's pure hydrocarbon. The one that have double bond is ending with a suffix -ane, and it's called alkane if it's carbon-carbon double bond. And the one that has triple bond is called -ine. That's what we have in alkyne. So all these hydrocarbons forming single, double, and triple bond are all as a result of overlap of the orbitals of those carbons and hydrogen. In such unique way, can form double, triple, or single bond. So this class activity 1. Why is a sigma bond stronger than a pi bond? Why is a sigma bond stronger than a pi bond? Why is a sigma bond stronger than a pi bond? Number one, why is a sigma bond stronger than a pi bond? Kezia, can you try? Why is a sigma bond stronger than a pi bond? Hello, Kezia, can you try?
So I'm not quite sure the reason why, but
Okay.
yeah.
When did you join the class? I've just explained those things now. Sigma bond is formed as a result of axial overlap. The axis of the orbiter is where they combine together to join. You get it? It's just as if, okay, your strength is in your hand, the strength of the other person is in his own hand, and you are joining hand together. It will be strong connection. You cannot be pulled away easily. That's the axial connection. So the sigma bond, which are single bond, are stronger than the multiple bond because they are formed at the axial overlap. However, the pi bond is not as strong as that because it's formed as a result of lateral overlap. I will show you. I'll show you what I mean now. Now, if you have p orbital of x is a dumbbell shape like this, but the axis of it will be along this as the x-axis. If you have another p orbital that have the strength of the electron is along the axis here. If the two of them are joining together at this their axis part, this bond will be a sigma bond, so it's going to be strong. However, if we have a p orbital not along the middle of the axis, but at the dope side of them, overlapping with another p orbital at the dope side, you can see just that tiny partial contact here, tiny partial contact here. It's just as if you have two human beings and you glue their leg and their head together. If you push them, they can easily fall. But if they connect their hand to hand together, you need a stronger force than what is holding those two hands together before you can disconnect them. So this is a pi bond. It's a lateral overlap, therefore it's not strong. But this is sigma bond, is an axial overlap and it's strong. That's why it's stronger than that. Say two conditions that are required before two orbitals can overlap. I've said that before. It's part of the lecture I just finished. What is the difference combination of orbitals that can lead to the formation of overlap in sigma and pi bond? The one that can result in the sigma bond are overlap between s orbital and s orbital, the overlap between s and p orbital, overlap between p orbital and p orbital. All other overlap, generally speaking, when the orbitals are overlapping, you form sigma bond. But the only overlap that results in pi bond is after the sigma bond has joined two things together. And you now discover that, oh, the first one has an unhybridized p. Oh, the second one has unhybridized p. They can now join at that position to form what the overlap that is required of them. Like, for example, if we look at this overlap between, let's say, an sp2 carbon. An sp2 carbon, we have S bonding with two p's. If there's another carbon also that have sp2, S bonding with two p's. You remember that p orbital is supposed to be three, px, py, and pz. But this one has only two p orbital. Now, it means that there is a p orbital pz that is not hybridized for this first. There's a p orbital that is not hybridized for this second. So when these sp2 overlap to each other first to form a sigma bond between those two carbons, then they already interacting with each other. So the PZ that is not hybridized, that is on this guy, and the PZ orbital that is not hybridized, that is on this guy, can begin to now feel the effect of each other to have a secondary overlap between them. And that's what results in sp2 orbital having two bonds between their carbon. The first is sigma, and the second a pi bond. This is the origin of all alkanes double bond. Every alkane's double bond is as a result of sp2 of one carbon overlapping on the sp2 of another carbon. And because it has not used all the three of the P's, when sp2 have overlapped on each other with a sigma bond, those two carbon can now say, oh, wait, I have a PZ that I've not used in hybridization. And the other guy also say, I have a PZ that I've not used in hybridization. So they can now do secondary overlap by connecting with their 1,1 electron to form the pi bond. So in every situation, if a sigma bond has not been formed between two groups to begin to relate and interact, pi bond cannot come on board. So sigma bond must be origin of everything. So the overlap that can result in sigma bond, it can be s orbital overlapping on another s orbital, as you can find in hydrogen and hydrogen. You know, hydrogen has its valency ending in s, it's 1s1. So this is an example of sigma bond. It can also be s orbital overlapping on p orbitals. That will also result in sigma bond. It can also be a p orbital, like aluminum is a p block element, overlapping on chlorine to form aluminum chloride. That will form a single bond between aluminum and 3-chlorine. All these are single bond. But immediately you are now having something like an sp2, which has already overlapped with a sigma bond. This can form a sigma bond, and in addition to that, you can form more pi bond. Why? Because sp2 has formed a sigma bond between these two carbons. But the first carbon has the third P that has not been used. The second carbon also has the third P that has not been used. After this sigma bond, then those two can now do a secondary overlap to form pi bond. That's why we say sp2 of hybridization will lead to sigma bond, and also in addition to pi bond. But if sigma has not formed, pi cannot come. So there are many requirements and many general overlap that result in sigma bond, but there's only one overlap that will result in pi bond. That is hybridization between unhybridized P on the first atom and unhybridized P on the second atom. Give at least one example for each. You can say I'm giving you that of hydrogen and hydrogen as S overlapping on S. Chlorine and chlorine. Chlorine is a P block element because chlorine have atomic number of 17, which is 1s2 2 p6 and 3 s2 and 3 p5. So chlorine is a P block element. If chlorine overlap on another chlorine, so it's like the valence shell ended in P electron for the first chlorine, valence shell ended in P electron for the second chlorine. So when you have chlorine gas, which is Cl2, it's as a result of one atom of chlorine overlapping on another atom of chlorine. So the question I've just asked you, these are the answers to them. The first one, if you remember, I asked you, why is sigma bond stronger than pi bond? Because the extent of overlap is greater during the formation of a sigma bond compared to that of pi bond. Because that extent of the sigma bond is axial overlap, and that of the pi bond is a lateral overlap. The second question we asked, state two conditions that are required before two orbitals can overlap. Half-filled orbital from one atom to combine with half-filled orbital from another atom, then form a new bond. That's a requirement. You get, for example, when you are looking at hydrogen atom has one electron. But hydrogen want to obey duplex rule. It means it needs 2 electrons in that shell to be stable and be happy. But it has only one. So that is like an half-filled s orbital. It will spin off. If there's another hydrogen coming closer to him and having only 1 electron, so that one can overlap on him by spinning down on him to form a full one. So that's why we are saying The R3 orbital of one combined with R3 orbital of the other can form a new overlap. The second condition is that atoms with bonding orbitals should be closely and properly aligned with axes of their orbital, because that's where the electrons are residing for overlap to occur. The question number 3, give different kinds of combination that result in sigma bond and pi bond. The first one, S overlapping on S, that's like hydrogen, which is an S block element overlapping on another hydrogen, that's H2. The second one is S overlapping on P. You remember that every element that have their valence electron ended in S orbital are called S block element. Group 1 and group 2 always ended in S. But group 3 to noble gas are P block element because they ended in P block. So when you are overlapping hydrogen on a group 7 element like chlorine, it's an S, which is hydrogen, overlapping on P, which is chlorine. Even if it is oxygen, oxygen is in group 6. Oxygen is a P block element. If S of hydrogen overlap on O, which is a P orbital, is an sp overlap. You can also have P to P overlap, like group 7 overlapping on another group 7, chlorine overlapping on chlorine to form chlorine gas as a molecule, and so many other examples. All these are examples of sigma formation, but the pi bond formation only occurs after the first orbitals overlap with sigma, then there can be secondary overlap to form that. So let's go to hybridization theory. Valence bond theory and molecular orbital theory cannot explain the formation of bond in some atom or molecule such as carbon and helium. This is the reason why things like hybridization theory comes to play. So where the valence bond theory and molecular orbital theory has failed to explain some things, then hybridization has come to support, to justify that. Example of that is in carbon and in helium. You remember that carbon has atomic number of 6, which has 2 core electrons and 4 outermost electrons. And you know every of the elements of higher member wants to obey octet rule, meaning that they want to have 8 electrons in the outermost shell. If they have 1, 2, or 3 electrons in the outermost shell, they will willingly want to lose them to become +1, +2, +3, and therefore we call them metals. If they are having 5, 6, and 7 electrons in the outermost shell, they will be willing to borrow 1, 2, or 3 electrons to become negatively charged. That is the non-metal. But now carbon sits directly in the middle of that 8, because in its valence shell, it has 4 electrons. You cannot relate with it as if you want to throw all the 4 electrons away to become C4+, or that you should borrow 4 electrons to become C4-. So the unique nature of carbon is what causes it to catenate and to form bond with itself in thousands of repeated units, as you find it in carbohydrates, in proteins, and in biomolecules. This is the problem why it could not be fully explained by valence bond theory and molecular orbital theory. Helium, for example, now, helium has atomic number of 2, which means it has only 1 shell, which it must obey duplex rule. And now with that 1 shell, you already have 2 electrons. It's not an half-filled orbital. It's a fully sufficient field orbital. He has obeyed the duplex rule. So he's not willing to lose in order for him to obey the rule. And he's not willing to gain in order for him to obey the rule. So he's already comfortably having his 2 electrons. That's why we say it's a noble gas. It's a rare gas. It's an inert gas. It's not willing to react, because reaction is as a result of interaction by either losing electron to make you more stable or by borrowing electron to make you more stable. But helium does not borrow and does not give. Therefore, he is not ready to interact under normal conditions. So that's where we use the hybridization theory to explain. And you can use it in other places too. But the place where you appreciate it better is where the valence bond theory and molecular orbital theory failed. So some conditions required for hybridization are stated here. Please, I want to remind us again, before every class, I will send the PowerPoints that we are to look at for that class on the virtual learning environment on your course page of this course. And I will also put the link to watch a YouTube video of the full explanation of that class. It's just less than 1 hour or around 1 hour video. If you watch it, it is self-explanatory. If you have any question for clarification in those are the ones that you will note and bring to the live class. I'm not supposed to still be teaching the live class as if I'm teaching explanatory class. This live class, for it to benefit every one of us, is to use it to solve problem in what you have watched in that video that you don't understand. Because doing this explanation here again, just as if I'm repeating the instructional video I've already given. So please, let's note it. I'll send it on that page again for you to watch the video before the next class. And please, let's tell others that facilitation has started. This is the second week for CHM204. And we have few number of weeks to complete. But if you are judiciously present throughout, I can tell you that you don't need to be running up and down when the exam is coming, because it is your full course material that are broken down into all this 1 hour class per week. So if you are able to go through all those videos and bring the problem you have to the class for us to solve, I'm telling you, the exam is a walkover, because I did not leave anything out of the course material that you are supposed to use. I've used it to pull out all of these each week's things you should learn. So please, let's make sure you always come to class and tell others to encourage them to come to class. Type of hybridization. There are in the carbon atom being a unique element, there are 3 types of hybridization that carbon can fulfill. If you remember the carbon atom, that the carbon itself, if you remember, carbon has atomic number of 6, which is 2 electrons in the first shell, 1 s2. That remains 4 electrons. 4 electrons, 1 s2, 2 s2, that's the second shell. The first orbital is still s, and the 2p2. This is the electronic configuration of carbon. Now, this is inner core. These 2 are the outermost one. Now, when you are looking at this, you discover that the outermost electron here is the valence electron, is the one that takes part in bonding. The inner core is in the nucleus inside, it cannot work. So the second shell is what we are saying. What we are saying here is that in the first shell of your carbon, that's 1 s2, you have 2 electrons. And in the second shell of your carbon, this is what you are used to in your secondary school. You have 4 electrons to make up the 6. However, if you look at it carefully, we discover that these 4 electrons in the outermost shell, in this shell form, you can't appreciate it better, because it will be as if they are all the same. But when you come to the mature electronic configuration, you discover that 4 electrons are from 2 different orbitals. 2 of them are from s orbital, while the 2 of them are from p orbital. So if you look at this shell of at the excited state, the 2s orbital is supposed to have 2 electrons at the ground state, which is 1 spin up and 1 spin down. And the p orbital is subdivided into 3. We have px, py, and pz. It must have maximum of 2. So at the ground state, the Hund's rule says, let the electron of these 2 p orbital enter singly before pairing. That means the first one will enter spin up, the second one will enter spin up. That is untrue. That is the ground state of carbon valence electron. So when you promote the electron to the excited state before the bond formation of the overlap, you discover that what will happen is that the 2s orbital is 1 electron spin up, and the p orbital, there are 3 of them. We have two spin orbital, spin up electron. So the one that spin down in the s orbital in the excited state will be promoted to spin up. So you can see in the excited state that all of them are half-filled, which is a condition for bonding. So in these three half-filled, we are saying it is possible for this S to overlap on all of the three P's. You see the PX, PY, PZ. When that happens, you have sp3 hybridization for carbon. It is also possible that the S can overlap with only two of the three P's. So the PZ will remain unhybridized electron. When that happens, you form sp2 hybridization, because hybridization is all about mixing, as if you are blending tomato and onion. The third condition is that it is possible for S to be blended or hybridized with only PX. When that happens, is formed sp. So in sp3 orbital, none of the p orbital is left unhybridized. That's why it is what you have in alkane, is complete saturation. In sp2 orbital, pz is not hybridized. That's what you have in alkane. So you can use that place to accommodate something else. And in sp orbital, pz and py were not hybridized. So you have two, that's why you have alkyne. Two more things to add to the sigma, make it triple bond. One more thing to add to sigma in sp2, make this one the double bond. And nothing to add to sigma in sp3, make it to be single bond. So this sp3 is what goes on in carbon-carbon single bond of alkane. This sp2 is what goes on in carbon-carbon double bond of alkane. And this sp is what goes on in carbon-carbon triple bond of alkyne. So the type of hybridization, as I explained, the bond angle expected between them, and the sp orbital is having a character, because when you say something is sp orbital simply means that it's using one s and one p. So if you want to use percentage there, s is 1, p is 1. For 100%, it will be s will be 50% character, p will be 50% character. It's two of them, 1 over 2 times 100. But if it is sp2, there are three entities there, S and 2 of the P, making 3. Each one of them will have 3.3 character. S will have 3.3, while P will have 67 character. But if it is sp3, there are 4 things there, 1 S and 3 P, making 4. So for S, it will be 1 over 4 times 100, that is 25. For P, it will be 3 over 4 times 100. So in sp3 hybridization, you have 25% of S character and 75% of P character. But in SP, you have 50% of S character and 50% of P character. So this is the second class activity. These are the second one. Explain how carbon combine to form methane, in spite of the fact that its electronic configuration suggests that only 2 bonds can be formed. The answer to this is in your course material in page 37. Number 2, explain the theory of sp hybridization in boron difluoride. The answer to this is in page 35 of your course material. What are the 4 limitations of the valence bond theory? You can see that in page 38 of your course material. The fourth question is that what is the percentage character of S and P in sp2 hybridization? When you say sp2 hybridization, of course, when you say sp2 hybridization, what we are saying is that how many entities form them? 1 entity is coming from S, 2 entities coming from P, making total of 3. So the percentage of S character will be, percentage of S character, it will be the total number of X over total number of the whole. That's 3 in total, times 100 over 1. While the P character there will be P is in sp2, there are 2 P's there. Out of total of the 3, it will be 2 all over 3 times 100 over 1. So that's how to calculate percentage character of S and P in sp2 hybridization. So, molecular orbital theory, it's supposed to be a kind of theory, and then it was proposed by Hans and Molliker in 1932. It involved the linear combination of atomic orbiter, and total number of orbiter we combine is total number of molecular orbiter that will be formed. These are the examples of it, where you can use it to fill in the bond into molecular orbiter, and you can use it to calculate the bond order. If you have this, there are different combinations that you can use. S combining with S, it will be a sigma bond. This is what I'm explaining. PX overlapping on PX is an non-hybridized P to form a pi bond, but S overlapping on P will form a sigma bond. So this is how to calculate the bond order. Please watch the video, and if you have any challenge, then you can bring it to class against next time. So we have been able to deal with number one, the valence bond theory of bonding molecules and condition for overlap. Number two, we have also looked at how atomic orbitals are mixed by hybridization to form bond. We've also talked about the different type of hybridization in carbon compound, which is sp, sp2, and sp3. Molecular orbital theory and the application is fully explained. Watch the video. And this mathematical expression to do combination of bond is also being explained. So at this junction, I would like to ask if you have any question before we call it a day. So on this note, we are